Hello everyone, my name is Mohit Gupta and I welcome you to my YouTube channel CAM Fundamentals. In today's video, we are going to discuss two important factors that affect Lee Chatelier principle that we forgot to discuss in last part. Along with that, we'll be doing some practice questions. The link for the previous parts are given in the description box as well as iCard over here. So without further delay, let's get started. So first of all, we'll be talking about the effect of addition of inert gas. So we know what are inert gases. Inert gases are the gases that do not react at room temperature. All the noble gases considered as inert gases, helium, neon, argon and so on. Along with that, nitrogen which form N2 gas and triple bond N that has very high dissociation energy and it does not react even at high temperature. So these are the inert gases. When introduced into a reaction chamber, they are going to affect the equilibrium. How? We are going to see that. So first of all, if the addition of inert gas occurs at constant volume, which means that you introduce the gas inside the chamber and its internal pressure increases. However, you have fixed the volume, due to which there won't be any effect on equilibrium. The next is addition of inert gas at constant pressure, which means the initial pressure which was 1 atm and the final pressure which is again 1 atm. Now, during this introduction of inert gas, no pressure increases or decreases. How is that possible? If you introduce a noble gas into the reaction chamber, then internal pressure increases. Now, to make the pressure constant, the pressure inside the chamber and the pressure outside the chamber need to be same. So in this case, the internal pressure increases, due to which the chamber expands, and on expansion the volume increases. However, the internal pressure become equal to the external pressure. So in this case, we can see that volume is increasing, and we know if volume increases, then equilibrium shifts to that side where number of molecules are more in amount. Okay, it can go either in forward direction or in backward direction depending upon where the number of molecules are higher. So here again I have made this table. In first column I have written change, then what is going to be affected, how equilibrium is going to respond, and at the end we'll be talking about the direction of equilibrium. So on addition of inert gas, we know volume of the vessel increases because internal pressure increases. What would be the response of equilibrium? It will try to fill the empty space with gaseous molecule. While doing so, where would equilibrium move? Equilibrium will shift in that direction where number of gaseous molecules are larger. So in order to understand this topic, we need to do a few questions that we'll be doing after some time. So next is effect of addition of catalyst. From the very first lecture of equilibrium, we are studying that catalysts do not affect equilibrium. So catalyst doesn't alter the state of equilibrium. It just helps the reaction to attain equilibrium quickly. So it increases the rate of reaction. Along with that, it also decreases the rate of reaction, due to which the equilibrium stays where it was, and it just decreases the time taken to reach to the equilibrium. So let's do a few questions. The first question is, which of the following equilibria are affected by the change in pressure? Now, how equilibrium is affected by pressure? If I increase the pressure, then equilibrium shifts to that direction which has lesser number of molecules. On a contrary, if I decrease the pressure, the volume increases and equilibrium move in that direction which has more number of molecules. So here we have four questions. Twice of HI is in equilibrium with H2 and I2. So HI is decomposing into H2 and I2. The number of moles on product side is 2 and the number of moles on reactant side is also 2. So number of moles on product side and number of moles on reactant sides are equal, which means delta n is 0. What is delta n? Delta n is the number of change in moles from product to reactant. In case of product we have 2 molecules, in case of reactant we have 2 molecules, 2 minus 2 is 0. Hence there won't be any effect on the equilibrium if we increase or decrease the pressure. In the next equation, we have two molecules on the reactant side and one molecule on the product side. In that case, delta n would be 1 minus 2, which comes out to be minus 1. So in this case, if I increase or decrease the pressure, the equilibrium is going to be affected. So how it affects? If I increase the pressure, the volume decreases and equilibrium will prefer to move in that direction which has lesser number of molecules, so it will move in the forward direction. If I decrease the pressure, volume would increase, and since volume increases, we need more number of molecule to occupy that space. So in that case, it will move in backward direction. In the next part C, we have N2 plus thrice of H2 is giving us twice of NH3. This is Haber's process, and then we are preparing ammonia from its elements N2 and H2. In the product side, we have 2 moles, and on reactant side we have 3 plus 1, which is equals to 4. So 2 minus 4 comes out to be minus 2. In this case, the pressure is going to affect the equilibrium. And now, which direction? If I increase the pressure, it will move in the forward direction. If I decrease the pressure, it will move in the backward direction. The next is SO2 combines with O2 to form SO3. In this case, the number of moles on product side is 2 and on reactant side is 3. So 2 minus 3 is equals to minus 1. It is also going to be affected by the equilibrium, and on decreasing pressure it will move in the backward direction, and on increasing pressure it will move in that direction which has lesser number of molecules. Let's move to the new question, another question. What would happen if two equilibria occur simultaneously? We have two equilibrium and they are occurring simultaneously. Two reactions are going parallelly and some amount of carbon monoxide is introduced during the equilibrium. So we have these two reactions, the decomposition of PCl5 which results in PCl3 and chlorine gas. This posine gas also decomposes to produce carbon monoxide and Cl2. So PCl5 and CuCl2 both are decomposing to produce these three products, PCl3, CO and Cl2. Now what we are doing, we are adding some amount of carbon monoxide. So if I add carbon monoxide, so carbon monoxide is on the product side. On addition of carbon monoxide, the concentration of carbon monoxide would increase. Now, what would equilibrium do? Equilibrium will try to decrease the concentration of carbon monoxide as we have increased, and equilibrium reacts in an opposite manner. So it will decrease the concentration of carbon monoxide. How? The carbon monoxide will react with the chlorine gas to form COCl2. So the concentration of COCl2 would increase. Simultaneously, the concentration of Cl2 decrease because Cl2 is interacting with the carbon monoxide to produce phosgene gas. So this in turn effect on the first equilibrium where we have chlorine gas. Now the concentration of chlorine is decreasing, which means the equilibrium of first reaction would shifts in the forward direction. Why? Because concentration of Cl2 is decreasing and equilibrium try to oppose it. So equilibrium will try to increase the concentration of Cl2, and what would it do? It will decompose the PCl5 to produce more PCl3 and more Cl2. So we have four options here. Concentration of PCl5 decreases, concentration of Cl2 increases, concentration of PCl5 increases, and concentration of Cl2 will remain unaffected. So option D is absolutely incorrect. Why? Because Cl2 is reacting and its concentration decreasing. So option B is also incorrect, which says Cl2 will increase. Now we're left with two options A and C where PCl5 is decreasing and PCl5 is increasing respectively. Here we have seen that on decreasing the concentration of Cl2, equilibrium moves in the forward direction and the concentration of PCl5 would decrease. So option A is correct. Now let's move to the next question, which is removal of N2 gas from the following system would result in. If we remove N2 gas from the following system, which is again Haber's process, here the ammonia is decomposing into N2 and H2 and we have to see what would happen. So here we have four options and we have to choose one of them. Now if I remove N2, the concentration of product would decrease. If the concentration of product decrease, then the reactant would decompose to increase the concentration of product. Because we are decreasing concentration of N2, equilibrium will shift in the forward direction to produce more of N2 and H2. So concentration of H2 is actually increasing. So option A decrease in the concentration of H2, which is absolutely incorrect. Lower partial pressure of H2, no, which means the concentration of H2 is again decreasing, which is not the case. And increasing the concentration of H2, yes, concentration of H2 is increasing. An increase in the value of equilibrium constant, no, this is also incorrect. Why? Because Equilibrium constant is the concentration of product divided by the reactant. Now we are decreasing the concentration of N2, which means the concentration of product divided by concentration of reactant is low. So the value of equilibrium constant would decrease. But technically we can't say the value of equilibrium constant. It would be the value of concentration quotient would decrease. The value of equilibrium constant would remain same at a constant temperature. So option C is correct. Let's move to the next question, question 4. What would happen if argon, air, which is an inert gas, is added to the following equilibrium at both constant volume and constant pressure? So here we have to find out what would be the effect both at constant volume as well as at the constant pressure. So equation is PCl5 is decomposing to produce PCl3 and Cl2 gas. At constant volume, as we already know, if we do not increase or decrease volume, there won't be any change, so no effect on equilibrium. However, at constant pressure, if I add an inert gas, its internal pressure increases, due to which the chamber expands. On expansion, the volume increases and equilibrium will favor that direction which has more number of. So in this case, more number of molecules are present on product side, therefore the equilibrium will shift in forward direction. The next question is, how will you modify the reaction condition to get maximum yield in this reaction? So in this reaction, you need to produce ammonia in maximum to maximum amount. So this is Haber's process, and the enthalpy of formation is minus 92.4 kilojoule per mole. The negative sign suggests that it's an exothermic reaction. So here we have to discuss about the temperature, pressure and concentration. How we are going to influence them so that we can get maximum amount of NH3. So first of all, let's discuss the temperature. The reaction is exothermic in nature because it has this negative sign. If I increase the temperature, the concentration or the amount of heat would increase here, so equilibrium will shift the reaction in backward direction, and we have to shift the reaction in forward direction. So in that case we have to decrease the pressure. So in terms of temperature, we have to decrease the temperature. So low temperature is required to move the reaction in forward direction. In terms of pressure, if I increase the pressure, the equilibrium moves in that direction which has lesser number of molecules. So in product side we have 2 moles and in reactant side we have 4 moles. So on increasing the pressure, reaction would move in the forward direction. So what would we do? We increase. Now, in order to maximize the concentration of NH3, if we remove NH3, the equilibrium will shift in the forward direction. So in order to get the maximum concentration, we have to remove NH3. More and more amount of NH3 would be removed, more and more NH3 will be produced during the reaction. Okay, let's move to the next question, which is very important. We have to predict as well as we have to explain how equilibrium is going to respond. First is volume of the reaction vessel is reduced to half. B part is helium is added, means a noble gas or an inert gas is added to the reaction mixture. The partial pressure of H2 is doubled. So in that case, the equation is given: carbon monoxide is reactant with the hydrogen gas to produce methanol. Delta H is minus 92.0 kilojoule per mole, which again means it's an exothermic reaction. So Kc, we can write the concentration of product divided by the concentration of reactant, and since the stoichiometry of H2 is 2, so we are going to square it. Similar is the case, we can write down the Kp, and in this case the H2 is going to be square. If the volume is reduced to half, now, if volume is reduced to half, the concentration or the molarity will become double. How? Let's see. Molarity, as we already know, it is the number of moles dissolved in 1 liter of solution, which is equals to N by V, where N is the number of moles and V is the volume of the solution. So now on reducing the volume half, the new volume will become equal to V by 2. On substituting the value of V in this formula of molarity, we'll get N divided by V by 2, and then which is equals to 2N by V. The N by V is already molarity, so we can write it 2M. Now the concentration of both reactant and product become twice. So in that case, we'll substitute the value. So we'll put 2 2 everywhere. This 2 will get cancelled by this 2 and we have 2 ka whole square. The 2 square, which is equals to 4, the QC will become 1 by 4 of this, and this is your KC. So we can say the concentration quotient is now 1 by 4 of the KC. Now here we can see that QC is lesser than KC, and in last to last video we have seen if the value of QC is less than KC, which means the reaction isn't starting and it has not reached to the equilibrium. So since QC is less than Kc and it wants to become equal to the Kc, it has to move in the forward direction. Next is if helium is added at constant volume. So if helium gas is added at constant volume, there won't be any change, hence no effect. The next is if partial pressure of H2 is double. So in order to do that, we can write the Kp, PCH3 and PCO, then P of H2 and its whole square. In this case, if we increase the concentration or the partial pressure of H2 by double, it will become 2 square, and that is equals to 4. So we can write Qp is equals to Kp divided by 4. Here again the Qp is lesser than Kp, and since Qp wants to be equal to the Kp, it will increase, it will try to increase, and to increase it has to move in the forward direction. So this is it for the today's class. If you like the video, please hit the like button. And if you're watching my video for the first time, then please consider subscribing. So this is Mohit Gupta signing off. Have a great day.